Presented is the video presentation for the project called Arrive Alive, AI-driven game made for the Business Intelligence course on Faculty of Technical Sciences at University of Novi Sad. Since the first time I heard about the Unity plugin called ML Agents, I wanted to try it out. I thought it was a great way to dig into reinforcement learning using a fairly user-friendly and documented framework and at the same time making an interesting game. Together with my colleague Obren Starović, I started developing the idea behind the game. The leading concept that we were striving for was creativity. We wanted to make such an environment that the agents would come up with their own ideas and somehow surprise us with their actions. After brainstorming for some time and discarding a lot of possible ideas, we settled on to the next one. The game was named Arrive Alive, since the players should arrive to the target spot without being killed. The environment is a construction site. There are 5 yellow bulldozers, trained ML agents, and 1 red player on the other side, a road roller, led by simple heuristics. The bulldozers are trying to get to their goal, the green square, while the road roller is trying to stop them in their intent by chasing them. If the roller touches the bulldozer is destroyed. Since the leading concept we were trying to accomplish is to get some sort of creativity in agents' behavior, we decided to give them some movable and unmovable props and obstacles and let them figure out the rest. Also, we added the score counter on the bottom to keep count of the current reward balance. As far as the reinforcement learning environment configuration goes, it went something like this. We gave 1 point reward for completing the run, -1 point for losing the bulldozer, either by falling off the edge or by being chased down. And the third reward was the time penalty. We wanted to make our agents faster, so we gave them negative reward for every step in the episode. In the beginning, the only observation our agents had was their raycast. With the raycast, they could spot certain objects containing certain tags, such as target, obstacle, or enemy. Rays had their length, so their eyesight was limited. For the actions, the agent could just alternate between rotating in one of 2 directions, clockwise or counterclockwise, while at the same time moving forward. We knew we wanted to start things slowly, using so-called curriculum learning. Curriculum learning is a way of gradually increasing the complexity of the problem, giving the model a chance to slowly develop, solving easier problems first, and then taking on harder ones. That being said, the first task we put upon our agents was just getting to the target spot. It didn't start off so well. Agents were roaming around, not really being able to figure out the task given to them. The problem was that the target was too far away. Agents weren't able to reach it with their raycast, so they never experienced the reward. Then we decided to make it even easier. We brought the target spot closely to the agent's spawning area. After initial random movement and exploration, after 70,000 training episodes, agents were moving towards the goal very confidently. When we moved the target further away again, the agents got into trouble. They couldn't figure out the location of the target spot since it was out of their range again. That's where we figured out that the information about the distance to the target, direction to the target, as well as the direction the agent is facing would greatly improve agents' behavior. Also, we decided to remove the time penalty, since we didn't want our agents to put speed too high on their priority list when the full game emerges. Things went smoothly from there. Roughly 200,000 episodes into the training, and agents were able to get to the target spot avoiding obstacles. As the graphs show, the agents quickly achieved the maximum reward of 5. Also, based on the episode length graph on the right, it's obvious that we were gradually moving the target spot further away from the agent, thus extending the episode length. And then we introduced the road roller. Roller had a simple heuristic for controlling the actions. Just chase the nearest agent in the area, knowing the positions of all agents at all times. The roller was just crushing our agents. Hardly any agent was able to reach the target, and if he did, it was by a lucky chance. We were hoping that the agents will come up with an idea, including obstacles, in order to cheat the roller, but after a few 100,000 episodes, that didn't happen. We knew we had to do something to help agents defend from the roller, so we came up with an idea. When the agents start moving, they can't be destroyed. They can still rotate and be pushed around, but as long as their movement action is in state 0, they are safe. In order to modify the agent's actions, we had to modify the model, and that means training the network all over again from scratch. So that's what we did. This time we knew exactly what we wanted to do, so we reached the same spot where we were before, a lot faster, and with a different model, the one including new action, staying in place. Also, we took the advantage of training the model from scratch and tweaked some hyperparameters of the network, one being the time horizon, which we significantly increased. The time horizon represents the number of steps of experience to collect per agent before adding it to the experience buffer and using it for updating the policy model. Since we didn't have frequent rewards within the episode, and the only positive reward could be won when reaching the goal, we set the time horizon to be big enough to capture all the important behavior within an agent's lifespan. We trained the model for 80,000 episodes more, and the agents started realizing the new property. If they stay in place, they can't be destroyed. They also can't achieve their goal of getting to the target, but at least their maneuver space got bigger. Sometimes they even managed to pull the roller off the edge while being pushed. 90,000 episodes later, the agent developed a strategy. One of them would wait for the roller and hold it close, while the others would run to the target spot. After training for 340,000 episodes more, agents become even smarter. They figured out that they can rotate the roller in place by controlling rotation and wait for the episode to end. With these new strategies, some agents were able to escape from the roller and reach the goal, but others were still being destroyed or being pushed out of the construction site. Then, the mean rewards stopped increasing, models stopped developing, and nearly 800,000 episodes, agents didn't improve at all. They weren't able to break the group reward of 2.5. Another property of the model that can be measured is entropy. A policy has maximum entropy if all policies are equally likely and minimum when the one action probability of the policy is dominant. In perfect scenario, entropy decrease should follow increase in reward, making the good choices even more probable. We noticed that the entropy stopped decreasing, and in the same time we wanted our agents to find new strategies, hence do more exploration. We decided to increase the beta, the strength of the entropy regularization 10 times, and see what happens. As we expected, entropy went up and agents were exploring around, not sticking to previous established behaviors. That decision resulted in this. Agents were performing worse than ever, even worse than when we first introduced the road roller. We were committed not to discard the previous 500,000 episodes of training, and when we were sure the entropy won't rise anymore, we started focusing on exploitation. We hoped the agents gathered a lot of information and that the gradual decrease of beta will, together with the decrease of entropy, make the policy model start focusing on the right actions and start increasing the reward. And that's exactly what happened. We settled onto a rule that we will keep the beta factor for as long as the entropy is decreasing. Once it starts to stagnate, we decrease the beta. That rule resulted perfectly in the mean cumulative reward, rising all the way to almost 4 points, which was significantly higher than the previous best results. As the graphs show, we had points such as 3.1 million and 3.8 million, where we reverted to the specific point in the training, discarding certain amount of episodes in order to keep the entropy decreasing constantly. In the end, with the beta parameter reaching 0 and with the reward stagnating, we decided to finish the training. After 4.1 million episodes of training, this is what we got. Agents managed to perform a perfect play. One agent is waiting for the roller and distracting it until other agents reach the target. After that, the remaining agent uses its rotation to manipulate roller's movement and virtually brings itself to the target spot without ever actually using its own acceleration. Even though we didn't achieve this type of perfection at every episode, with this we concluded the project.